Great. Yeah, somehow Skype broke down. Also yesterday I had problems with Skype. I do hope it works now for the lecture. Welcome back to blockchain-based system engineering. Here I added more the overview slide, to remind me where we are. We are today here on this day. We will talk about Ethereum Basics. We also more or less halfway through the lecture. This part I think is very stable. We did it now 2 years in a row. That's more or less the very stable and basic knowledge you need to understand blockchains with the example of Bitcoin. And now we move to another platform, to Ethereum. I think Uli already mentioned Ethereum in the exercise on the 3rd of June. I will tell you today about the Ethereum Basics. What is the general concept? What's the network architecture? What's the goal? What are the limitations? And then we learn more about developing smart contracts. Maybe also today I can start on this. This will then go on. We talk about software development with Ethereum, with design patterns, how to integrate, how to develop distributed apps with the browser, and also exercises for all of this. So this is the most closest thing you can get to web application engineering, that we say now we have a framework, we have a language, we have an execution model in the cloud or in the internet, and on top of this you can then develop applications which are blockchain based. Therefore the name of the lecture, blockchain based software engineering. At the end of the semester we then will move on and to talk not about public chains but about consortium chains or private chains or permission chains, as we want to name it. So therefore we have 2 lectures on Hyperledger, also again basics and applications, and then also 1 lecture and 1 exercise regarding Corda, which is also an increasingly popular platform, and which we added this more or less to the lecture. We also have then a very nice, now confirmed, and also with the speaker, external lecture, where we want to tell you more about this very magical thing, and it's really a little bit like magic, the zero knowledge proofs. What are they as a black box concept? What are they useful for in the future for blockchain-based systems, both public chains in particular, but also private chains? And then we are ready for the exam. We are currently a little bit struggling with the exam format, but we will keep you updated. We don't want to talk about intermediate states, which maybe only confuse you, but I'm rather sure that next week or so we will have a very clear picture of how the exam will take place. Okay, let's move on with the lecture. I go now to the first slide deck, these basics. Okay, so it's all about what is Ethereum. And we will talk first about the Ethereum ecosystem. As usual, if you talk about, let's say, programming languages or databases, and you make a choice, what's a good platform and what's a good programming language, or what's a good database system, or what's a good middleware, you look not only at the technical system itself, but why is it relevant? Who is using it? Which vendor support it? On which standard is it based? How is it different from other offerings? And therefore, we start now outside in, that we first talk about the ecosystem of Ethereum. Where does it come from? What are the technical papers? What are the foundations? What is the uptake? Who is using it? In which volume? How is it evolving? And again, if with blockchains, that's rather easy to measure by the network measures. Then we move on to the system architecture. What's the basic idea? How is it different from other ideas, in particular from Bitcoin? And again, you have a good idea, I think, what it could be. And then we move on to the network architecture before we then go to smart contract development and programming. The history is, again, for computer science, it's already 7 years old, which is in computer science terminology a long time. If you compare this to physics, they are laughing. It has been developed by Vitalik Buterin, a rather young guy, and he's also a very charismatic person. Something like with Oracle, you have the founder of Oracle, you have Bill Gates. So, and again, we have some little bit Bill Gates here with Vitalik as one person, which is more or less very much driving the whole development. Yeah, he announced it in January 2014 at a Bitcoin conference, and then he started the public crowd sale, and therefore this was more or less collected a lot of Ether, which were sold in exchange for Bitcoins. Yeah, and so therefore more or less it was a bootstrap process based on a cryptocurrency. And that's more or less the Ethereum that has been sold at that time. And you see, it was rather interesting. Yeah, that there was a lot of uptake of people which said, "Okay, this is a good idea, and we want to buy it and we invest in it," which is a good start. Yeah, because if you have a large number of people which are invested in your coin and in your platform, they are people which more or less are multipliers, yeah, which talk good about the platform because they are now invested in it. But again, this is the let's say people part or the financial part and the buy-in part and the ecosystem. But now we want to talk as a computer scientist about the technical aspects. And again, the nice part is that the technical aspects are nicely defined. Yeah? It's not just let's say a very vague white paper, but a rather precise white paper. You can find it here under this URL, which is more or less this seminal paper, yeah, a next generation smart contract and decentralized application platform. And I think it describes it very nicely. All of these systems we are using here, which are programmable, are platforms in the sense that they provide an infrastructure that can be used by others to build their applications. Yeah? Therefore, it's not a data platform, but or a service platform, it's an application platform. And it's different from, let's say, something like Azure or Google App Engine in the sense that it's a decentralized app platform. Yeah, that's the next better description what it is. And then the other words may be a little misleading, that it's the next generation, everything is next generation, but indeed I think decentralized application platform is a big leap forward. And it uses now this strange word of smart contracts, which we already alluded to, which is more or less the idea that if you develop applications here, they are called, or the elements with which you develop these applications, or the components, are smart contracts. Okay, so again, this document has written initially by Vitalik himself alone. It contains both a high-level description of the functionalities and also a summary of all the platform and technology. Yeah. So therefore, it's more or less makes it accessible. Yeah, what is it good for? Like something like a language report, etc. It's also updated because Ethereum, like Bitcoin, also evolves. Let's say again, initially it evolved more quickly, yeah, but now I think it's rather stable. So therefore, it can be compared with JavaScript to a certain degree in the maturity level. There more technical information is available in the yellow paper, which has been published by David Wood, yeah? And it more or less defines the technical specification. Yeah? If you really want to build it, yeah, let's say if you want to use, let's say, MongoDB or MariaDB as a user, it's different from if you want to build it, extend it, or analyze it. Yeah? So therefore, if you want to better understand what's the technical specification of the language and the bytecode, etc., you then should consult this description, which more or less, let's say, contains, for example, the bytecode mappings, yeah, which is really the specification how to build a full node. And here again, it's mostly based, yeah, as typical as a specification document. Yeah, it follows more or less the implementation, and it doesn't talk so much about use cases. It's more or less more dry paper. Okay, the next point is now if you have a decentralized platform, it's different from having something like an Oracle database, because or a core media content management system. In core media, there's a company which owns the code and which decides, the company decides what will happen with the code. If you have a decentralized platform and you have to build trust in this platform, it's a very bad idea if the platform is owned by one company, yeah, because then you have a very centralized governance structure for that platform. So therefore, a very typical move for all decentralized platforms is to create a foundation. Yeah, so that's the idea that you want to have more democratic decision power, how the whole system develops. Yeah. And so therefore the foundation is now a legal thing, which has been founded in Zug in Switzerland, because the laws in Switzerland are rather suitable for such foundations. It's also more or less Switzerland as a country which typically has the image of sticking out of, let's say, all the wars. It should be not seen as an American company, it should not be a Chinese company, it shouldn't be a European company, or it should be maybe a world company. So therefore they decided to do it in Zug. And the mission of this foundation is to promote and support Ethereum, and in particular the platform, the base layer research, the development of the platform, and also education as we're doing it, to bring decentralized protocols and tools to the world that empower developers to produce next generation decentralized applications, dApps, and together build a more globally accessible, more free and more trustworthy internet. So that's more or less the mission statement, which is typically, you have a vision for decentralized, then they have a mission statement. If this is a decentralized world, what's the mission of the company or of the consortium? And then you build more or less governance structures to implement this mission. It's a non-profit organization. Nobody should do it for the purpose of money. It's also a foundation. It's not something like an Aktiengesellschaft where you have stocks and you have different ownership rights, but it's more or less run or owned by the people which are members of the foundation. The foundation then got a lot of initial funding, which was raised, maybe even all. Uli maybe knows more about it, how many things went directly to the foundation and which ones are still with the founders. And it more or less runs more or less the development, more or less, in the sense, as an open source project, more or less, would be the closest thing you would compare it to. Okay, if you now look at the usage, more or less, of Ethereum, we have statistics here. You see this spike, let's say, of Ethereum, which was more or less at the same time when we also had the spike here in Bitcoin. Bitcoin, as you may have seen, had, let's say, waves, let's say, of speculation here, whereas Ethereum more or less is at a moderate level. Again, it has a lot of fluctuation here, the price. It's not really stable, also on a daily basis, and also it fluctuates around here. And if you follow more or less the media, there are always discussions whether the true price and value should be here or the true price should be zero. It's a very controversial discussion whether this is a very good solution, in the sense like JavaScript. It will rule the decentralized world, because it's the earliest development and the most thought through language with the highest user base. That would be the reason that it should be very highly ranked, like the first Bitcoin, the first digital Bitcoin currency. Digital currency is the first one, even if it's not the best. It's the early adopter and it has the largest buy-in. And similarly, you could argue that Ethereum is the best smart contract language because it's the first, like JavaScript is the first, let's say, browser-based language. And it became finally the dominant browser-based language, despite many attempts to replace it. That would mean that these high prices are justified. You could also argue, it doesn't scale, it doesn't solve all the problems which are necessary, and sooner or later it will die, a much better platform will be there. Okay, so if you now look at the network metrics, you can see the active wallets, how many people use their wallets. It's not dead wallets. You can also look at the history. So therefore it's still increasing, not really exponential here. That was a big uptake phase. Now it's more linear. Maybe it's students of courses which learn to program with Ethereum. That would be maybe the most negative interpretation here. And you also can see the number of wallets, of unique wallets, with at least one incoming and outgoing transaction. So again, you cannot really compare the size. They are not normalized to the same level, but you see more or less the development here. Again, like Bitcoin, Ethereum also uses the proof of work. So it has all the negative implications the positive implications of proof of work, that it's very good to bootstrap the system. It's very resilient to attacks, but it has the negative aspect of the high energy consumption, depending on the actual use of the system. Yeah. And now, again, if you want to look at the activity of the network or the activity of the infrastructure, you would look at the hash rate in the proof of work, and therefore you see that it now is rather at average level of activity. Again, if you look at the hash rate, you see here the exact numbers of May. Uli is very kind to do updates here. And currently, it's mostly used, graphical processing units are used for hashing, because it has an ASIC-resistant proof of work, that you cannot use tailored hardware for doing this. But again, if you look at the annual electricity consumption, it has this enormous amount of terawatt hours for the whole year. If you want to know more about the energy consumption, we provided links to these resources, and also if you want to look at the current network hash rate, here's the source where you can find this chart. Okay, so this essentially says the ecosystem is alive and kicking. It's not exploding, it's not ruling the world, but I think it has a very strong position in the blockchain community. Yeah, so if anybody talks about blockchain systems, there's no way of avoiding Ethereum. So now we go one step further to the system architecture. And I think I mentioned this already in the very first lecture. So it has a very simple, but also very attractive model. Yeah, because the simple model is, imagine there would be only one computer. Yeah, one single computer. Yeah. Therefore, you wouldn't have any interoperability problems, because all the programs that run on this world computer, by definition, can also interact with the other programs on the same world computer. And if you know how to program this world computer, you more or less can program all of these applications. You don't have to learn different installations of this world computer, different variations of the world computer, different language quirks like in JavaScript, or different historic things. It's one world computer, which is more or less sufficient for doing all the necessary data management, the necessary computation, and the necessary interoperation of these different parties. And the world computer can be used, it's an open world computer. There are no limitations who can deploy code on this world computer, and there are no limitations who can more or less interact with the programs that run on this world computer. Yeah, so therefore it's a rather, how would you say, extreme, but also interesting concept, yeah, because it more or less says, yeah, why distributed computing? Yeah, if the world computer is distributed, we don't have to talk about distribution and network latency and transaction failure, because this world computer has transaction safety. Yeah, it's as good as the best Oracle database, because you have transactional execution model, and you don't have to think about network failure, you don't have to think about transaction aborts, about lost messages in a network, yeah, because distributed communication is done behind the scenes, because you can now talk to a lot of these nodes here, which are the nearest to you, so therefore it's also a very resilient system. Yeah? So therefore it's, I think, a very nice value proposition that will stick around. Yeah? So therefore the properties are, all participants use the same computer. If you want to interact with the computer, you write transactions, yeah, in a small script, and execute this small script on this computer, and either the whole script runs successfully or it fails and is rejected by the world computer because it has a bug, or it's illegal code, for example, etc. What's also nice is if people have some state here, like in a Java program, they can decide whether they want to share the state of their program with you. It's an abstract data type. They can either expose an interface, and you can only do push and pop on their state, or you can read the state and you can read variables and you update variables like in a database. Yeah, so therefore everybody shares the same resources and storage, which is also very interesting, because you don't have to do remote database access and convert JSON strings to Java objects and to relational tables. It's one execution model and one data model. The computer also doesn't have an explicit owner, that's the idea. Nobody can stop you from running the programs, and even if a large part of the world is denied to run the computer, the other part of the world can then take over these other people and can make this a very resilient system. Then the question is, how does it work? And again, it's all about money here, because we now have the same idea with Bitcoin, that you get a reward for running nodes that support this computer. And if you get these coins, these currency for the world computer, you can reinvest it to run future programs. So therefore, there's also a clear benefit. It's not like a Bitcoin purely speculative value, but it has real value because it's this money makes this computer run the execution. Therefore, you can measure the value more or less of these currency. If you now want to run, for example, so how would you use such a world computer? Imagine you want to run a fair election. So therefore, the idea is you would want to have something like a contract, which looks like a Java class, where you say you have an election contract, and the election contract more or less essentially has a state, and this state essentially says we want to collect votes for different candidates. In our case, we want to have two candidates, Amabo and Pemurt. That would be, if you turn it around, it's Trump and Obama. And then people could now vote. So therefore, they would now say, I want to vote for Amabo, or I want to vote for Trump, or Pemurt. So that would be the only option people have. And therefore, they could now vote for this party and increment the counter for that party. That's the idea, that we now want to run elections by more or less running this program for a limited time period, and everybody is allowed to participate in the election. So that's the idea now, that we would deploy this contract, which essentially would more or less create an initial state where nothing up to now happened. Then one person would execute this code and would say, I want to execute a transaction which consists, and the extraction is very simple, it only performs a call of the vote operation with the parameter Amabo. So that's the idea, that I want to execute this transaction. And after the execution of this transaction, successful completion of this transaction, we have a new world state. The initial world state was empty, and now we have a world state where we have Amabo with 1 vote and Trump with 0 votes. Then the next, and again, since this is a transaction, there's no concurrency control problem. Either this person now gets the right to do the first vote. So therefore, you don't get concurrency issues that now 2 counters are incremented and you get all these problems of shared variables in main memory. If you have 2 threads which want to access the same variable and you increment the counter, this is a very dangerous operation in main memory if you have multiple threads. And now it's also maybe dangerous if you have millions of users which want to concurrently vote, that these counter increment doesn't lead a concurrency conflict. So therefore, this is also handled by the world computer because it serializes all these transactions. So therefore, there's now a serialized order of execution. Then some other person can now do is vote and so on. And so with each vote, we now create a new state and we keep the whole history as the blockchain, what were the previous votes and what was the sequence of votings that led to this total vote. Which is also a very important concept. That we now combine the idea of a world computer with a world computer which has full traceability of all previous transactions that have been ever executed on this world computer, similar to the whole transaction history of Bitcoin. And you get the idea. Now we do this again, we get a new vote, etc. What's nice about this is we not only see the votes and the result, but if you now voted, you can check whether your vote has been counted, because you can go back in the history and see, okay, actually the computer executed my vote, And since this is a Bitcoin blockchain, nobody can more or less remove this fact from the history. Yeah, and that makes it a very nice data structure and execution model. Okay, and so this is more or less the transition we showed on the previous slide. And now if you look at the blockchain, we make now this naive assumption that each block contains only one transaction. You would see now that we now extend the blockchain, and the blockchain now contains these transactions, and therefore you get the correlation between the tamper-proof storage of these transaction records. In reality, obviously, multiple transactions are put into a block, similar to Bitcoin. Okay? Okay, now the question is, how do I program this computer? What's the programming language of this computer? And the idea is, like with any other decent programming language, that it has two levels, the answer. One answer is, okay, there's a programming language which is targeting programmers, which is human readable and easy to read. It has a syntax, it has a semantics, it has a compiler, it has a debugger, where we have a mental model how this is written, the programs, as a programmer, and then the tools give you the illusion that you execute these programs on a hardware. That's more or less one level of the answer. Yeah? It's the language definition of Ethereum, and the execution semantics. It's the language definition for Solidity, the programming language of the Ethereum, and it has the execution semantics of this language. Unfortunately, it's very hard and tedious to define the execution semantics for high-level programming language, which is as expressive as Ethereum is. So therefore, instead of doing this and doing it down to mathematical operators, you say, no, we have this high-level programming language, but this is compiled into bytecode, and this bytecode has a much limited instruction set. And so therefore, based on the bytecode instruction set, we can define the execution semantics of the Ethereum virtual machine. Yeah, so therefore, we now have an Ethereum virtual machine, which is similar to the Java virtual machine, which now allows me to define an execution model for state changes of the blockchain. Yeah. So therefore, we can now formalize, also in mathematical ways, the Ethereum virtual machine as a tuple of a state. Yeah? So if you want to understand the current state of the world computer, we would say, okay, we have the block state, which is more or less the history of the current blockchain, yeah, the past execution history. It's the current transaction which should be executed. It's the current message which should be executed. It's the code to be executed. It's the main memory which is available for the execution of the transaction. It has a stack counter. It has a program counter, and it has gas. And gas is more or less a counter how much energy you are allowed to consume for the execution of this transaction. That's the idea, that you now have a virtual machine, and the virtual machine can be described by this data structure, which more or less defines more or less the virtual machine's state, and the persistent memory, the main memory, the execution stack, program counter, and the available resources for this transaction. And the block state is this, let's say, like a database. Yeah? It contains all the global state of the whole blockchain, including all accounts of other users, all contracts that have ever been deployed or are currently running, and storage where these contracts store their state. Arrays of data structure, records of data structures, that's the storage. Okay, so therefore the block state now is can be visualized like this. It's the blockchain, back to the Genesis block, the past execution history, the current accounts controlled by a private key, and all smart contracts, including their storage. If we now execute a transaction, that's more or less the second concept we need, and I already mentioned it in my previous slides. A transaction technically is a signed data package that is always sent by a wallet. Yeah? It's the same idea with Bitcoin, that if you want to execute a transaction, you simply say, okay, this is the transaction I want to execute. I sign it because I authorize it to run in my name, This gives you more or less access control, like if you run on a Node.js server, then you have to have an access privilege for the Node.js server. If you have allowed to access certain data structures on this Node.js server. So therefore, the same data package both says, I want to execute this voting transaction. And by the way, it's me because I signed this transaction. So therefore, this transaction consists of the recipient of the message, a signature identifying the sender, which is you, the amount of ether to transfer from the sender to the recipient, and an additional data field. And a start case value representing the maximum number of the computation steps the transaction execute is allowed to take, and a gas price value representing the fee the sender pays for the computation steps. And that's what is the basic data structure. Yeah? So therefore, a transaction is something like a record of this information, signed, including your signature, that you authorize to do this. And in particular, you want to do now two things. You want that the system is executing the transaction, and only if the execution was successful of the transaction, you are willing to pay money to the receiver in exchange for running this transaction. Yeah, so therefore, a transaction has now more or less three purposes. One is what should be executed, and you authorize to do it, and you also authorize that money is spent for the execution of this based on this gas price, and you authorize this transaction to run only for so much. You give it some gas, some let's say amount of execution power, and the third thing, you also authorize the transaction to take place. Yeah? So therefore, in the extreme case, you could use the Ethereum virtual machine only to transfer money because you don't execute any code. You simply denote a recipient of a message and an amount you want to transfer from the sender to the recipient. Then it would be only used as a coin transaction. Yeah, it's a wallet-to-wallet transaction. Or you want to execute a transaction which executes a contract, and the contract then decides what should happen. Yeah, so you don't simply say do this, yeah, give money to this person, but execute now this contract in my name, and the contract will decide what to do with my money, what to do in my name. Yeah, so you authorize something like an agent to do things for you. Yeah. And that's these two kinds of transactions. Yeah, so a wallet-to-wallet transaction simply for doing financial transactions, and wallet-to-smart contracts more or less to enable now a smart contract, a program to decide what to do, to vote for you, or to buy something for you, or to invest in something for you, or to do a very complicated computation for you. Okay. And important is the idea that a transaction has this transaction semantics you know from databases, because if the smart contract fails, you don't want to pay money for a failed contract. So therefore, only two things have to happen in one bundle. Your money is spent and the contract is executed, or no money is spent and no contract is executed. Yeah, so therefore, you don't want to have a smart contract which starts and then fails during execution. Yeah, which is different from Java programs. If you start a Java program and it does some side effects and then it crashes, the side effects are not undone. Yeah, whereas if you have a database and you start a database transaction, you do some database updates and your transaction fails, then the things you did are undone. This is exactly the semantics of the Ethereum virtual machine. Yeah, it has transaction semantics. Yeah, so therefore, a transaction is a bracket of with asset property. It's done all or nothing. In a serialized fashion, it's isolated. Yeah, it's in serialized fashion. It's durable because once it has committed, it will survive. Asset, yeah, is durable. Yeah, these are the asset properties. And similarly here, the money transfer, either all the money you want to do goes to the receiver, or it stays with you. But there's no situation, even if the network crashes, that some of your money is spent and other money is not spent. Okay, there's a second concept now, because typically if you execute a smart contract, more often than not, this smart contract is not as simple as we had it with a voting contract, which executes one statement, but mostly a contract or a program calls other programs. Yeah, that's more or less an important concept in programming. that you build programs or services or contracts, and then you build more complicated programs, services, or contracts by combining existing elements. Yeah, so therefore what now often happens is that you execute a transaction on a smart contract, and your smart contract says, okay, I now want to use the services of another smart contract, yeah, to maybe get information about the weather. Therefore now I don't write the code to get the weather, but instead of this I use a service of somebody else that now provides me weather data. And maybe the weather data service now decides not to do the weather himself or herself, because she again sends a message to another smart contract. And then the results go back, and then the money is spent, is distributed between these parties. So therefore, we now have a transaction at the beginning, which starts the whole thing, and then we have a lot of messages between smart contracts, and only if all of these things are successfully executed, these changes of all these smart contracts are confirmed. Yeah, and otherwise nothing happens. Yeah, so therefore a message is very similar to a transaction, and messages are only sent by contracts between contracts. Yeah, if a wallet doesn't send a message to a smart contract, it sends a transaction to a smart contract. And therefore also the messages contain the sender of the message, which is implicit, yeah, the caller more or less of the transaction, the recipient of the message, the amount of ether to transfer alongside the message. Yeah, and this is also an interesting concept that you don't simply say, I want to get weather data, but I want to get weather data and I'm willing to pay so much money for it. Yeah, so therefore there's always an economic incentive for this contract owner to decide whether to do this, or you can also, let's say, use this money for money transfer here. Now that's more or less the ether that is transferred, and an optional data field and a start gas value, and the start gas value essentially says, let's say if you run this program in your name, how much are you willing, how many resources are you willing to pay for the execution of the smart contract? Now that's the start gas value, you can limit this. Okay, so therefore these messages are now data objects which you can inspect and look at them. Yeah, so therefore it's not just a call stack like in Java, but it's really a message queue or message stack that you can look, each smart contract can look at the message that invoked the smart contract to find out who's the sender, what's the amount of ether transferred, the optional gas data field, and the start gas value. Okay, so that's more or less the basic idea. Yeah, you now have this world computer. The world computer has many contracts. Then you have the wallet owners. The wallet owners send messages to one of these, sends a transaction to one of these contracts, and this contract starts execution and maybe then decides to invoke other contracts, and then this is the whole game. If you want to now just understand how the virtual machine works, it's a classical stack-based machine. Therefore, you now have a code which is a byte code. Yeah. So therefore, it's very similar to what we've seen with assembly code or what we've seen with the Bitcoin script bytecode. Yeah, for example, here again we have a sequence of bytecode statement pushing a value on the stack, pushing one value on the stack, doing a memory access, pushing something on the stack, calling something, doing a comparison operation, pushing the result, and do a conditional jump to a certain location, and here again pushing something. Yeah, so that would be a typical bytecode program. And in order to understand what the bytecode is doing, you would have to have a stack data structure, and you have additionally also non-persistent storage, which can be used for temporal computation during execution of a contract. If you want to compute the Fibonacci number, or you want to compute, let's say, some array matrix multiplication, you do this in memory, you don't do this on the blockchain. The stack contains now more or less the program counter and the core stack. Yeah, it's a fast, non-persistent buffer to which 32-bit values can be pushed and popped during execution. And the program counter points now to the location of the current instruction that is being executed. Yeah, for example, here program counter 2 would point now to the memory store operation here. I already mentioned gas. So gas is more or less the more or less equivalent of the energy consumption you want to spend you want the amount of energy you want to give to a program. How long is it allowed to run? This is important because you want to achieve two things. One thing is you want to avoid that you have infinitely running programs. For example, if you write an infinite loop while true do something, that would be a bad idea because it would block the world computer. If an infinite loop is on a world computer, it would more or less block the world computer. So therefore, the world computer has to decide when a computation terminates, and the easiest way to achieve this, to have this gas which goes with the world computer, and whenever the world computer executes an instruction, let's say memory access, addition, computation, gas is consumed. And once the world computer runs out of gas for your transaction, it aborts the transaction. It says it's unsuccessful because it was running too long. So therefore, it's important that you more or less give enough gas to a contract, not too much, or not too, because then many people could use this gas to consume your money, but not too little, because otherwise the contract would not be executed. There are also some incentives for programmers which are implemented by negative gas. For example, imagine you have a data structure, you have a program which now creates megabytes of storage on the world computer, and it occupies a lot of memory, main memory, but also persistent memory. Then there should be incentive to give this memory, to free this memory. And this is done by giving negative gas to people which clean up if they have temporary data structures, and they free now these temporary data structures, that they get gas back, so that they don't you don't get memory leaks in your programs. Okay, I think this is more or less the basic idea of gas. And then there is now, gas is the unit of, it's for example, if you have a specific operation, then there's a very well-defined formula how to compute the gas you earn here with the self-destruct, or the gas you have to spend for multiplication, for example. So therefore, gas is a unit for computation, but additionally you want to pay for it, and that's defined by the gas price. So therefore, this is very fixed for a program. But maybe now you have seen with Bitcoin, you are willing to pay more gas. So if you want to make the world computer run your programs with preference, you would say, by the way, dear world computer, I'm willing to pay a gas price of 500. And then the other people say, I'm willing to pay a gas price of 400. And others say, I'm willing to pay 1,000. Then the world computer can decide which of these transactions are executed with higher priority. So therefore, again, this is the same idea with the transaction fee of Bitcoin. There is a dynamic game going on between the world computer and the users of the world computer. How much are they willing to pay for programs to be executed? And that's also a nice idea which has been taken over from Bitcoin. Okay. Any questions so far? Okay. Easy, fine. Then we can move on to the account types. Again, I think Uli already mentioned this in the exercise, that Ethereum uses an account-based ledger. So contrary to this non-spent transaction output we have in Bitcoin, we have a rather simple account-based ledger, where Ethereum, for example, if a coin, invent a new coin on top of Ethereum, then it would be implemented by big arrays saying which account owns how much money. Similarly, as you have seen it for the voting algorithm, that we have a big table for all the candidates, and for each candidate we have a counter how much votes the candidate has. So therefore, we have an account-based ledger for Ethereum. Again, these wallets are identified by an address, and these addresses then represent a unique account. And we now can have two kinds of accounts. We have accounts which are controlled by private keys and owned externally by users. So these are wallet accounts. In order to work with the money, you now have to sign transactions with your private key. And so therefore, this is the way, more or less, how to move then money between your accounts by having a private key for this externally owned accounts. The other idea is that you have now, so these would be humans, or external programs. And the other thing is a smart contract is now something which is cool. It's something like a legal entity, which is also allowed to, if you have a company, not only humans can be have rights and obligations in our German law or worldwide law, but also organizations like foundations or universities or companies are legal persons, and they also can earn money, and they can have rights and obligations. And the same thing, a similar thing happens now in smart contracts, that you have now a code, smart contracts, and the code of these smart contracts decides what should be done with the money the smart contract owns. Yeah, so therefore this is the nice idea, that a program can, like for example, there could be an agent which represents a car, and the car could earn money by driving and could spend the money for going to the repair shop. Yeah, that's the basic idea. You would found a company on the blockchain, and the company owns money. The company is represented by a smart contract, and you can donate money to the company, or the company can earn money by providing services, and you can also use the money to pay to other people which work for the company. And that's the idea, that a smart contract also can own money. Okay, so therefore smart contracts are account entities on their own. They also have a unique address where you can identify the contracts, so you can distinguish smart contracts and people from each other. Contracts can send messages to other accounts, both externally controlled and smart contracts. So therefore a machine can now spend money to a human, and a human can send money to a machine, or humans can send money to other humans, and machines can send money to other machines. However, smart contracts can't issue transactions themselves. Yeah? So therefore, transactions are only things which come from externally owned wallets. And again, a smart contract, as we have seen it with the voting smart contract, or if we later on will see token contracts, they have a persistent internal storage which keeps track of their state. Yeah? Like a database, that a database knows, keeps the state, even if the smart contract is not being executed. If we now talk more in detail about what is an account, then we can formally define an account as a combination of a nonce value, a balance of the account, a contract code, and a storage. Yeah? So that's more or less an account. Yeah? It's more or less something different from, let's say, unspent transaction output, which is more or less associated with an account, but it's really a data structure that is more or less persistent. Yeah? So it consists of a nonce, which is an increasing number. This is attached to any transaction to prevent replay attacks and double spending. Yeah, so it's important. If you now execute code and you want to make sure that not somebody else uses the same transaction history to re-execute the code, therefore you use this nonce value in the transaction, so that you have to have new signatures and you cannot do replay attacks. Then you have the balance, which talks about the current account balance of this account in Ether. You have the contract code, which essentially says what's the bytecode. Yeah, you remember this bytecode is simply data, and the bytecode is now represented as a contract code here. And if no contract code existing, then it's an externally controlled account. And then it also contains a storage. And so that's more or less the code, and this is now the data which is available for the account, and it can be dynamically allocated by the code. Yeah, so therefore, by default, it doesn't have storage, but the constructor of a contract could then create storage, which will be used to store, let's say, maybe the voting results or the matrix multiplication results. Okay, I already mentioned that the blockchain itself uses a point of work algorithm currently. The vision is later on to switch to more smarter and scalable and not so energy consuming algorithms, using things like forking the Ethereum blockchain. But currently, it's the proof of work algorithm, which is called ETH hash. Yeah? And it has been designed to be ASIC resistant. Similarly to Bitcoin, the difficulty for mining is adjusted over time, but here it doesn't take, I think, 10,000 blocks, but it's adjusted after each block. Yeah? The reason for this is that the Ethereum blockchain needs much more speed of executing these transactions, yeah? Because if you execute a program, a lot of blocks are being generated, transactions are being generated, so therefore they decided to do now the difficulty adjustment after each block. There is no actual block size, which is limited, so instead of limiting the size of a block, you want to limit the complexity of a computation that is being executed, or the complexity of the execution. But gas also computes the main memory resources, limits the main memory and persistent resources can be used. So therefore, by setting a gas limit, there is a natural limit that you don't get infinite large blocks because a transaction runs for 15 days or something, or 500 years. So that's the idea, that this gas limit, because gas is expensive, leads to natural upper limit of the block sizes for transactions. Again, we have now these race conditions in this distributed network. As you remember, what we explained in detail, but for Bitcoin, that maybe there are two virtual machines running, creating a legal transaction, but in the end, in this consolidation process of the proof of work, some of these transactions have to be undone. Yeah, so it's the same things happen with Bitcoin, that if a transaction successfully completes, it may be the case that with a certain probability there will be another transaction or a deadlock or a conflict in the Bitcoin blockchain, so that a new chain has to be created, and that this non-valid block, this so-called uncle block, becomes invalid. Yeah? So it's the same property as we have seen it with Bitcoin. You as a programmer execute a transaction, then you get the message, yeah, it has been successfully executed, but then maybe 6 blocks later you get the message, oh, sorry, there was a conflict, we had to roll back your transaction. You get back your money, all side effects of your transaction are undone, but maybe you have to wait now until enough blocks are on top of your transaction. Yeah? So that's the same thing here of the Ethereum blockchain, that it's not as final as a database transaction. Yeah, if you have an Oracle database transaction and Oracle says it has been stored, and later on the server crashes or the hard disk fails, Oracle promises you that your transaction is durable. And the durability of the Ethereum blockchain is not immediately durable, but it has this with infinite probability that if you have 6, 7, 8 blocks on top of your terminated transaction, then you can be sure that it will, with 0 probability, be undone. Okay, so therefore this is now this idea of how long do you have to wait for the finality of your transaction. And also there's a different reward scheme here, that these uncle blocks, that even if your block becomes an uncle block and the result has been included in the final chain, the miners get mining reward for that. Yeah. So therefore, this is more or less one different design decision in Ethereum. Okay, let's look at the time, but I don't tell you too much at high speed and you sleep. So once we now understood the proof of work algorithm, we can talk about smart contracts. Yeah, and I think we now talk about it a little bit black box-like, and then we will talk later on about the instruction set and how to code smart contracts. So from the outside, a smart contract is a set of functions that can be called by other users or contracts. Yeah? In this sense, it's very similar to an object which has a set of methods which can be called by other objects or users to execute some functionality by an object. Yeah, so The smart contract can execute functions like addition, subtraction, hashing, like a normal programming language, or do and or not. It can send either or store data. So this is the typical things like storing data and executing functions like in function programming language. But in addition to this, you have a built-in operation to send ether to other people. So therefore, it's an economic machine, more or less. Each smart contract is an account-holding object. So therefore, it has its own address. So it can also store ether here. And smart contracts have some peculiarities compared to traditional software, which we now allude to. Because since smart contracts own money, I think one thing is obviously interesting. If they own money, how do we protect this money? So therefore, we talk a lot about security and access control. Who is allowed to interact with the contract? How do people authorize against this contract, etc. So therefore, the development of smart contracts requires special attention on security, because once you wrote a contract, which maybe has an error, this contract is more or less out there in the wild. Everybody can call it, everybody can use it, and so therefore, and everybody can analyze what the code is and can try to find bugs in your code. So therefore, people can see the address of your code, they see the opcodes of your code, and they also see which functions you have and which signatures you have. So therefore, they could try now to run your code and with their addresses and with their accounts to more or less squeeze something money out of your contract. Also, the people see the whole history of your contract. So who called it, with which arguments did people call it, which also gives people a good insight what can be done with this contract. So therefore, security is a very high concern. I think what's also now important is what's now similar or different with other programs. And one important other concern is that smart contracts should be closed systems. So the idea is, and closed means the following. If I execute twice the same smart contract with the same parameters on the same world state, it should yield the identical result. That's a very important point, because they should be deterministic. That's one reason why they should be closed systems. A second reason why smart contracts should not depend on external systems is that if they wait for external systems, also the execution duration for a contract may be extended. If a contract says, now read a file or write to a database, the database or the file may be temporarily not available, or it may take 2 minutes or 2 seconds to execute this operation. I think you know this from JavaScript. If you have long-running transactions, that's also a timing problem and a stability problem, because if the other long-running transactions fail, then the whole system may fail. And the whole world computer would be blocked if you wait for external data. So therefore, this is the reason why smart contracts are closed systems. Or these are the two reasons why smart contracts are closed systems. To summarize, smart contracts can't access any data from outside the blockchain on their own. There are no ways, let's say, of opening network connections, opening sockets, writing to files, reading from files, reading external main memory, looking at the screen. And that's the idea that you achieve truly deterministic behavior, and that you also don't get, let's say, time delays in the execution of the world computer. So now you wonder why are these very useful programs? You have a program, you run the program, and the program then returns a result. So that would be typically what you do with functional programs. And if you look at all functional programs that people come up with, they are mostly very boring functional programs, in the sense that these functional programs do computations and they don't have any side effects on the world. As most programs you write in your life are writing hello world, opening a door, closing a door, looking at the screen, getting keyboard input. So most programs you write are interactive programs. So therefore, we now have to understand that now smart contracts seem to be not very interactive. But this is, I think, not really a problem, because the interaction now can be done by people that want to interact with smart contracts, that they issue transactions from the outside to these smart contracts. So therefore, it's always possible that external parties and the world outside influences the blockchain, the smart contract, by sending transactions to the smart contract. But the smart contract cannot send transactions to you as a user or inform you about something, or it cannot read the temperature. So instead of this, to achieve now the same idea is they use so-called oracle contracts. So the idea is, if you have a smart contract which depends on external information, you assume that somebody else wrote this oracle contract, and this oracle contract contains the data you're looking for. For example, the temperature in Munich, or the age of Professor Mattes, or the current number of people in a certain room. That's the idea. You assume that magically this contract has this knowledge. Then you request this data. You also can give money to get this data. And then the contract decides whether it gives you the data and returns the data to you. And this is then on-chain code. So this can be done and verified. And whenever you do the same thing, the oracle contract would yield exactly the same results. It's a purely functional program here. On the other hand, the assumption is that somehow this contract knows my age or knows the number of people or the current temperature. So therefore, the assumption is outside of the blockchain, there will be off-chain some program, which is called an oracle service, which now takes this data from an external API or from the sensor or from some main memory data structure here to read the data and write this data to the oracle contract. And then also, and the data comes from external web API. So I first get the external data off-chain. This off-chain oracle service reads the data with an ordinary program. This program returns a result, or it's a REST service. It returns the data. And once the data has been read, it's written to the oracle contract. And the oracle service does this on a regular basis, or there are different ways of doing this, which we will discuss later, but this allows us to more or less to get access to external information through the oracle contract. What's also nice with this oracle is that in order to interact with the oracle contract, this oracle service has to have an identity. So it has to have a wallet. So therefore, if you now analyze the history of this oracle contract, you can see what is the history, where does the data come from. And also the oracle contract can earn money for providing this data. So therefore, there's incentive for the oracle service owner to not cheat and provide wrong data, because if it would turn out that this oracle contract is cheating and sending wrong data, people would cease to send money to this oracle contract because it's not a trustworthy contract. So again, by introducing money into the game and to play these programs over and over again, you have a game theoretic situation where cheating is not a very nice option for these oracle contracts. Okay, that's, I think, a very important concept, how to do in blockchain-based software engineering, that you always know who was cheating, because it was this service. And you also can give money to people which don't lie, so that it's beneficial for them not to lie. Okay, now we can move on to the programming language, because you don't want to program. So I think you can use bytecode to interact with the blockchain. And there are several research projects which do this. They compile, let's say, Python into Solidity bytecode, or Ethereum virtual machine bytecode, or Haskell compilers which compile Haskell into Solidity bytecode, Ethereum bytecode. But the main programming language that has been designed for Ethereum is Solidity. Here we have an example of a small Hello World program in Solidity. First we look maybe at it, and then we talk about the general properties. So it starts with a pragma that it says, okay, I am a program which should be compiled by a Solidity compiler with version 0.4, 2.4 or higher. Yeah? So an important point here is that since we generate persistent programs, which may be smart contracts which will be still active in 100 years, we have to be sure that in 100 years the right compiler is being used for compiling these programs and interpreting these programs. Yeah, so we assume that the Solidity language will change its character in the future. And so it makes perfect sense to also, when we write programs, say, by the way, we assume that this program will be compiled by Solidity. It is based on the language specification 4.24 or the compiler version 4.24 for Solidity. And that's the first thing we are talking about. It's similar if you write persistent data structures in a file. You always say, okay, by the way, this is a Word file of version Word 7.7.7.6, so that if a later version of Word opens this file, it can more or less do the necessary conversions to correctly handle this file. So that's, I think, a nice point to see that from day one, this is a persistent programming language. Then it looks very similar to syntactically to JavaScript or Java. It uses curly braces for block structuring. Therefore, a contract is something very similar to a class definition. And instances of a smart contract are similar to objects. So therefore, you have a distinction between a contract, which is an instance, and a contract definition, which is a class. And so therefore, this is what the class definition. And the class then can define a constructor, which is more or less a famous public main method, where you now where you can construct an instance of a Hello World contract. And the constructor doesn't take any parameters, and the constructor uses the default initialization. It doesn't do anything. Now that's the way how you create from a Hello Smart contract a new instance of the Hello World smart contract. And that's done by this constructor. Once you have this new smart contract, clients can now can also create a transaction, which calls now the render Hello World function. Yeah, so therefore, class consists of methods, smart contract consists of a collection of functions, and here we have a render Hello World function, which takes no arguments and returns a string. Here we write curly round brackets because unlike JavaScript, or unlike Java, Ethereum allows me to return multiple values simultaneously. Yeah? And here we only want to return one value, so therefore we write that it's only one value which is being returned. And the value we want to return is the Hello World value. Now, that would be the minimum viable Hello World program. And there's obviously nothing like printf, because printf would be something which interacts with the environment, and this is strictly forbidden for smart contracts. So therefore, the only way, more or less, to return something is as a result of my transaction. So a smart contract essentially computes a value, or a collection of values, or a list of values, and it may have side effects on other smart contracts, and it may transfer money between smart contracts and wallets. So therefore, it's an imperative programming model. Let's go to the left. So what are the language properties? This whole thing is statically typed. If you write this, you have a type checker which at compile time validates that this is more or less returning a string, that this return statement returns a string, and that this is correctly type checked, and that the constructor has the right number of arguments, blah, blah, blah. And all scoping rules are statically enforced. It's object-oriented in the sense that you have encapsulated state. We don't see state here, but the constructor may have variables here, and these variables are all accessible to the functions. And so therefore, you get this object-oriented notion that objects have an object identity, which is the address of the contract. They have state, which are the variables, and they have behavior, which is modeled by the functions. And they can also link to other objects because you have one smart contract can have links to other smart contracts, which now gives you more or less a network of objects which communicate through message passing. Therefore, it's object-oriented. You also have the notion of inheritance, that more or less Hello World can inherit from already existing contracts. You not only have calling relationships, but also inheritance relationships. We also have very complex user-defined data types, which are rather nice. We have public and private methods, so that a contract may have methods or functions which are only accessible to the contract itself or to subclasses of this subcontracts of this contract, and you can have public methods which can be called externally. We also have dynamic binding. You can have a collection of objects, for example, a collection of smart contracts, and they are of different type, and you have heterogeneous collections, and then you can iterate over the elements of this heterogeneous collection and invoke a method, like print yourself or rotate or pay money, and then different pay money, rotate, or print yourself methods are being executed. So therefore, if you send a message to an object, it's not the object itself decides which implementation is to be used. This is not statically bound. And the whole thing is compiled to EVM opcode instructions. Let's look at the time. That's fine. Okay, now we want to look not at a Hello World example. No, we will do this later. What are typical use cases for smart contracts? We just name them here. We don't show how they're implemented. I think one use case which is obvious is that you use it for token systems. And this is also the largest use case currently for Ethereum, that you can implement your own coins, more or less, and tokens on these blockchain. You can have your Florian coin or your charity coin or some friendship coin. That's possible by defining this through smart contracts in a very nice way. And therefore, this allows you to create your own currency and token systems on top of the Ethereum blockchain. And how this is done, we will talk later. But that's the most valid use case currently, which is the reason why there are so many transactions. Most of them are token transactions and payment transactions. The second thing what you can do is you can create an identity and reputation system. So the idea is that you create now something like companies or institutions or services on the blockchain. A weather service, a calculation service, a game, a lottery, and then you more or less create now these lottery contract that has an identity. It has a certain reputation that people more or less certify that once they played the lottery, it seems that the lottery is fair. That would be a typical other thing that is being done with smart contracts. Then there is this idea, which is still a very, it's both. It's an idea and a real implementation, which is called the decentralized autonomous organization. I mentioned this already in the beginning of the semester. The idea is that you now have a multi-signature wallet, which is not owned by 3 CEOs, but it's owned more or less and regulated by smart contracts. And these smart contracts define rules under which the company can earn money, and under which conditions the company can spend money. So therefore, essentially, you can write now the constitution of an organization, and the constitution of the organization is written down as smart contracts. And the constitution of the organization is then run by Ethereum, by the Ethereum network. So therefore, you now create a decentralized autonomous organization, because once you started the organization, you don't have any control more as a person of the founder of the company, because the only thing the company will do is now execute these contracts, and now people can now decide whether they want to do business with the company, call their functions, become maybe an employee of this company, or provide services to this company, and that's the idea of a decentralized autonomous organization. And again, we show you the example of the code later in the semester. We also talked about election and voting systems, because as we have seen, by the nature of the Ethereum blockchain, you can not only see the current state of the vote, Trump was the winner, and believe us, he is the winner, but you can see who voted when, with which result and how the accounting was done in the past. Here, one picture to this idea of the decentralized autonomous organization. So the idea is, if you look at a company, for example, a new startup, the new startup essentially has an idea, a business idea, a business vision. It owes money, and it has contractual obligations with its environment. For example, typically, the founders more or less have rights. The owners, investors, they more or less have the right, more or less, they have the obligation to pay money to this company that is founded, that it can start working, like the GmbH, 50,000 euro. But then they also have voting rights. So therefore, there are smart contracts which regulate the rights and obligation of owners, investors towards this company. Once a company is established, it can hire managers, a director, etc., or CFO, or an accountant. That would be now contracts between the people which have to do certain services for the company. Then the company could start hire staff, other staff. It could sell services and data to customers. You get the idea. So therefore, the idea is now that you now can write more or less all the contracts which establish an organization, and an organization is nothing else than a collection of contracts, to do it on-chain. Actually, we currently pitching for a study with one well-known expert in law, of company law, organizational law, Gesellschaftsrecht in Germany, for the Bundesjustizministerium, because they want to know, is this a stupid idea or is this a good idea? How would you run an Aktiengesellschaft or society or GmbH or a private company on a blockchain? So therefore we do studies how this could be done, what are the limitations or opportunities if you do this on a blockchain-based AG, a blockchain-based Genossenschaft, a blockchain-based GmbH. And again, the vision is a little bit, I therefore have these two books here, because this idea of this decentralized organization, which more or less lives longer than the managers, the owners which founded it, has already been discussed in this science fiction novel by David Soares. It's, I think, a very nice book. I read it first, but I didn't know the connection with smart contracts here. And the idea here also is that there was a crazy person establishing a company which is now fully autonomous and which hires contractors to kill people, or which builds machines to build a decentralized economy. That's more or less the main story here of this Daniel Soares book. And also here there are really people which say it's very bad that, let's say, a very limited number of people own Amazon. Wouldn't it be nicer that Amazon is owned also by the customers of Amazon, so that we have a cooperative here, so that we more or less have decentralized organizations which serve the people, which are not serving only the owners, investors, but which also serve the customers. So because if the customers, if Amazon gets rich, also the customers get rich. If Amazon wants to change their payment scheme, the customers will know we don't like this, or they would vote. And based on the vote of all these shareholders, and not only the shareholders, but on the vote of all these beneficiaries and interest groups, we could build better organizations. So therefore, I like this idea because it really is nudging and says, okay, it's all about money here. There's still this money. The main reason of this company to survive is to have sufficient money to incentivize these people. But the money is not only owned by one typical scheme like a shareholder company, that dominant players have more money, can get richer, but maybe it's possible to build now companies which limit this centralization mechanism. I also show you the second book. It's a German book, unfortunately. I don't think it has been translated into English. It's a senior historian, I don't know what's in English, a person who studies and teaches history, and he looked at stories of the past in Germany since the Second World War. What were visions of the future, or dystopies of the future? The acid rain, for example, the oil crisis, the nuclear power future, that we will be all very a nuclear power plant company, world. Yeah, and he more or less reflected on what is the history of all these visions of the future, and which of these visions became reality and which of these visions never materialized. And that's, I think, is an interesting question. This sounds like a very interesting future, which might have very nice properties, which balance a little bit of socialism, communism, and capitalism. But it still has to be seen how likely it is that this future will come. So therefore I mentioned this, that a lot of also this motivation of people to engage in decentralized economy is building a better future for the world. Okay, now we can, I think, yeah, sure. Hello.
Okay, we got some questions on Moodle, on Tweetback. We start with the first two ones. I think they cover roughly the same idea. And it's about gas and gas consumption on Ethereum. And why does Ethereum have another abstraction in the form of gas? Couldn't it be possible to formulate transaction using Ether alone and throw away the concept of gas?
Yeah, good question. I try to explain it, but I do it now again. So the idea is, if you define the language and the virtual machine, you want to have one fixed rule that says, okay, if you do a multiplication, this is 5 gas. If you do a matrix multiplication, it's 500 gas. If you allocate 5 gigabyte of storage, it's so and so much gas. And if you deallocate it, it's so and so much gas. So the idea is you want to have fixed rules for gas computation, which are very deterministic and don't change over time. On the other hand, you want to achieve financial incentives to the miners to execute a transaction. And as you have seen it, yeah, so therefore, like Bitcoin, if there are a small set of miners and there's a lot of demand of executing transactions, it should be beneficial for the miners to get more money for the same amount of computations. Yeah? And this is the idea that you have this gas price, that you say, okay, here's my code, and the code, if it's executed, will use the very same amount of gas. And so therefore, the miner would typically look at the code and say, this is a profitable transaction or it's not a profitable transaction, and make the decision based on the code. But you now want to give an incentive to the miner to say, yeah, I know it's my vote, but I want my vote to go in today because there are hundreds of people and the voting will end in 5 minutes. I want to be sure that my vote goes on. Yeah. There's a token sale, there's an auction, and I want to make sure that my vote and my bid in the auction goes in early. And this is the idea of this gas price, that you then say, okay, it's a vote, but my vote is more profitable for you as a voter, a miner, to do this. And this, I think, has a very nice idea, because then you get the optimum price for executing this transaction. You know?
Yeah. Okay. Thanks. Next question is the equivalent of accounts. So it's about account-based ledger versus transaction-based ledger. What would be the equivalent of accounts in a transaction-based ledger? Would it be the unspent transaction balances, or what would be the equivalent there?
No, also the equivalent. So if you look at, the idea is, if you look at the blockchain in Ethereum, in the blockchain you would see data structures which look like arrays, like Excel spreadsheets. Yeah, there would be a big Excel spreadsheet saying Peter, the wallet ID of Peter owns 50 tokens. That's the state. The state on the blockchain is organized as an Excel spreadsheet, like a table, a mapping from wallets to the current value of this wallet. Yeah, in this point in time. Yeah, or maybe if you go back to Obama example, if you look in the blockchain, we see currently Obama has 5 votes. That's the state. Yeah, that's transaction state based. Whereas if you want to find out what the current amount of money Peter has, or what the current number of how much money Peter has in Bitcoin, you have to go back the whole history and you have to look at the main memory data structures if you then executed the whole transaction history. Yeah? So therefore, that would be then the unspent transaction output, and the unspent transaction output is the available money, which is on the market. But if you want to know the exact account one person owns, you would have to do the calculation from the beginning on in history. Does this answer the question?
Yeah, I think so. The next question is about nonces and in the account-based ledger. And in this context, what are replay attacks? If we would miss the nonces, replay attacks would be possible. What's going on there?
Yeah, so I think the general idea of nonces, let's say, even if you look at sorting of hashes, is that you say there's a computation which I will do over and over again. So therefore, if I did it in the past, people could simply say, I look in the past when this computation has been executed, and then I know already the result of this computation. Yeah? In order to avoid this, you now artificially make this computation different by adding some sort value or some nonce value, so that if you re-execute this transaction and you do it hashing or you do signing, etc., you would get different values. Now, that's the basic idea. Despite the fact that you know technically the same computation should be done and the same action should be done, you want to avoid that people can take now the record of your information or the knowledge about the past execution to more or less cheat. That's the basic idea.
So this nonce, in short words, prevents the transaction from being executed again, because this nonce is only allowed to exist once, and you have to increase the transaction counter. And the next question is, am I correct? If we use self-destruct in the contract, it will destroy the current contract, which is no longer accessible in the future. And the student thinks, isn't that contrary to the assumption that a blockchain is immutable?
Yeah, I think you have to distinguish two things. One is the history cannot be changed, but you can change the current state. Yeah, so if you go at the Obama example, so at a certain point in time, so obviously the state of the contract changes. Yeah, so here the state 3 of the contract, the state 2 of the contract is different from the state 3 of the contract. Yeah, so therefore the history consists of the whole history of states, which makes it traceable. And now if the next thing would be election self-destruct, there would be state 4, where the election is self-destructed. But the fact that state 4 has a closed, so here somewhere we would close the election. And if the election is closed, it's closed, but we still could find out what was the state of the history. So the votes would not be changed. Yeah, so a self-destruct would create a state in which this election is no longer accessible. Yeah, we can no longer vote and add to it, but the past history of this election is not changed.
Yeah, that's true. So the history does not change, but the state can change. I get a further question about oracles. And the question is, we have an Oracle smart contract on chain. And how does this Oracle smart contract verify the Oracle service?
How does the Oracle contract verify? No, the idea is, if we will see this later, the Oracle contract more or less will distinguish, if you look at the code, it has two user groups. One is the user group of users which want to get data, and the other one is the provider group or provider person or provider credential, which is allowed to write data to the Oracle contract. Yeah, so therefore, if you look at the contract, it essentially has to say, I have 5 methods or something, or it has a request data method and it has a write data method. And obviously, the request data method can only be called by consumers, and you have to make sure, and there you would be rather liberal and say everybody can ask me for data because I give it to you and I get money. Now, that would be the incentive of the Oracle writer. But then the Oracle would say there's an owner of the contract, and only the owner is allowed to write data to it. Yeah? And in order to check this, we have now built in access control in Ethereum, which we will talk about in the next lecture. so that the Oracle contract can verify that the caller of this write data operation is a wallet owner, which he knows because it's himself. Yeah, so therefore, the wallet owner, only the contract owner or the person creating the contract would be allowed, if I write the code here, to do it, or they could also delegate this right to other parties that they are allowed to write it. But how to define access rights, how to delegate rights, we will show in the next lecture.
Okay, and then our last question for today, and I think then we are finished because time running out. A rather more high-level question. Do you think the voting with Ethereum could be used, for example, for the Bundestagswahl?
Unfortunately, today not, because essentially what we know, if we execute this here, is it? So it's hard to tell who is this guy. Yeah? We know the address here. Yeah? So therefore we know this wallet cannot vote twice. So he normally would check that the person don't vote twice. So therefore I think so the smart contract can ensure that people don't vote twice, and that the fair election, it can also make sure that the vote only runs for a certain time period, etc. But it cannot verify that these are German citizens, which are at least 18 years old, and etc. And that one citizen doesn't have two wallets, etc. That's one problem we have, and that's the identity management problem. I'm still rather optimistic that the state sooner or later will realize that it would be beneficial if they would provide oracles, something like the Bundesdruckerei or the other oracles, which allow me to have a verified identity or multiple identities here, self-sovereign identities, which I could connect with my Personalausweis, and that would be then achieve the right result. Yeah? That I would more or less, with the oracle, the election could make sure that a certain wallet address, which is a trusted party, in this sense, the Bundesdruckerei, says this is Florian Mattes, and then it would be possible, and also it would verify that I'm 18 years old and that I'm living in Munich, and then based on this, I could then run this election. Yeah? That's, I think, the basic thing which is lacking, the link between the blockchain identity, which is my wallet, and my real identity, which is typically my birth certificate and the combination of all my physical properties. And so therefore, I'm very optimistic that sooner or later, the digital mysteries, etc., will push for a world where we can do this. We get digital credentials here, which allow us to do more sensible things like voting for as owners of a company, voting as a student in a student council. These are all things that could nicely be done with blockchain-based systems. Oh. So we last week we stopped here in the Ethereum Basics, and I simply want to show you the network architecture. Yeah, we spoke about, let's say, the history about Ethereum, the idea, and the execution model in general. And again, it's very similar to Bitcoin. You have the so-called full nodes, which more or less are this distributed network. The full nodes, more or less, are often, let's say, run by a mining pool provider, which distributes the mining puzzle to pool participants. And therefore, this is similar to Bitcoin. You also could have solo miners, which run a full node on their own if they're very rich and have the necessary equipment, but they are possible. And otherwise, you can also have light nodes, which simply follow the network to get more or less a picture of what's going on without mining and contributing new blocks. Right? Simply observing thing. If you're a researcher, for example, or you want to do analytics on the blockchain, you can do this with these light nodes. And again, there was a criticism a little bit in that there's too much text in the slides, and I agree, they are not slides. I would, if it's only for presentation purposes, but the benefit for you is, and for us, we only have one document, yeah, which is also the script. Yeah. So therefore, this what I said is repeated here, so that you also can have it in textual form. Again, these nodes are then called. So the implementation now consists of two things. So typically, you have a command line tool, which you run as a process on the server, which doesn't have a user interface. So you essentially run this node and it has RPC interfaces to interact with it, but also in a command line interface. But it's like a MySQL database. You would start a MySQL database daemon in the background, and you would not directly interact with it. Yeah? So, but on the other hand, if you now want to more or less observe and to try out things and interact with the systems, then you would run clients which have a browser-based front end like OpenEthereum. So therefore, these are then called Ethereum clients. Yeah, I would call them peers a little bit, so that you more or less have nodes and you can see what's going on. And where you have more or less a visual interaction with the contracts, which makes it easier also to let's say, for starting and debugging and testing purposes. Okay, then the question is, how do the nodes find each other? And again, these clients contain a list of default peers, which are hard-coded in the source code. And otherwise, you could also start them with the command line argument so that they connect to one other peer in the Ethereum network. And so therefore, this is more or less where you can see it more or less in the source code. What are these addresses more or less so what are the ways you look up new nodes so that you more or less, you start now with the hard-coded nodes, the hard-coded nodes then provide access to the new nodes so that the network more or less can find out who are the peers and who are the members. It's this peer discovery process.